Hi, and welcome to our second lesson concerning rational functions. Today our topic is going to be slant asymptotes. You may recall from yesterday's lesson that the final rational function that we graphed had a look similar to this one, where you can see that there are two distinct parts of this function. But they're not broken up like in 90-degree segments. It's broken up into slanted segments. So slant asymptotes is what our focus will be today. Let's take a look at this. We can see that there's a vertical asymptote at x equals 2 unless this function happens to have a removable discontinuity or factorable discontinuity. So I'm going to just take a quick second. To factor this, we'll need the x and the box, and you can see that I've started already. I have the box here. I've entered the 2x squared and the positive 1 in their spots. I need things that multiply to make 2 times 1, or 2, while they add to make negative 3, and those would be a negative 2 and negative 1. Now in the box, since we've got that value other than 1, we've got to put in here negative 2x, and in here negative 1x, or just negative x. Now we're looking at greatest common factors, and you can see that a value of 2x can come out from here. That would leave an x here. X times negative 1 will get us that minus x, and 2x times negative 1 will get us that we need. The two factors then are x minus 1 and 2x minus 1. This is not a removable or factorable discontinuity. So we don't have to worry about having a hole, but we do have a vertical asymptote at the line x equals 2, and that would be right in here. Whoops. Right along in there. But you can also see that there's a slanted line of avoidance, and that's what we want to talk about today. So slant asymptotes, folks, they occur when the function rule for a rational function has a degree in the numerator that is exactly one bigger than the degree of the denominator. Say that again. It has to be exactly one greater than the degree of the denominator. To find the equation of a slant asymptote, you just divide the numerator by the denominator. You disregard any remainder. That doesn't matter, but the quotient part that you get, that's going to be the equation of the slant asymptote. So let's try that for the one shown on the previous screen. I'm going to use synthetic division because that's my favorite. So the coefficients are 2, negative 3, and 1. We are dividing by, the factor is x minus 2, so we divide by positive 2, drop and multiply, add and multiply. And the remainder is negative 1, but again, that does not concern us. What does concern us is this. The equation of that slant asymptote will be the line y equals 1, and the degree, remember, will be 1 less, so 1x minus 1. Y equals x minus 1 is that slant asymptote. I'd like to show you that our work is correct by verifying on the calculator. I have our function rule in y1, and I put the equation y equals x minus 1, which we said was the slant asymptote, in my y2. I've set a window that's similar to the graph that you see on the paper, so here we go. Here comes our function, and you can see it mimics very well what we have. Then the line y equals x minus 1 is indeed that oblique line that cuts right through. I want to have you try that again, and so I am going to ask you to stop the video. I want to have you find the asymptotes, both, well, we should check and see if it factors. We're going to do the whole 9 yards. We want to check and see if we have a removable discontinuity. If not, then we want to talk about a vertical asymptote. We have a degree here that's exactly one bigger. That means there should be a slant asymptote. So will you pause that video and find them, please? Sketch them into the picture. Here's my work. This is not the top is not factorable. The signs are not correct. In order to get negative 4, you could use negative 5 and positive 1, but that will make that sign be incorrect. So it's not factorable. There is a vertical asymptote then at x equals 3, which I have sketched in. To find the slant asymptote, I divided top by bottom, and this is just a coincidence that it happened to come out to be the same line, y equals x minus 1. Now before I try and sketch the graph, I'm going to take a look. I don't know for sure what this is going to look like, although I have a sneaking suspicion it's going to be here and here. I want to check to make sure. So I put it into my y equals. I set up a window that's exactly like the window on your screen, and let's take a look at that. Yeah, my supposition was right. Okay, the graph does come here and here, and that line of avoidance again, y equals x minus 1. Very good. Let's move on. And I want to give you a couple of chances to pull this all together. This is our goal, to be able to sketch these rational functions based on what we know about what the families of functions look like, how asymptotes work, using tables and calculator tables and graphs if necessary. So I'm going to ask you to first off pause the video and solve this problem, please. Very good. Here's my work. There is no factorable or removable discontinuity here. So there are vertical asymptotes at -1 and 1, which I've sketched in. The horizontal asymptote, I did a little work here. I know the degree on top is 1 less than the degree on the bottom because there are 2 powers of x here. So I showed the division, but I know that if the degree on top is smaller than the degree on the bottom, that horizontal asymptote will be at 0. Again, this is the proper procedure to use, but if the degree on top is smaller than the degree on the bottom, your horizontal asymptote will be at 0. There cannot be a slant asymptote since the criteria cannot be met. The degrees are wrong here. So as far as where this function fits in, I wouldn't know probably without looking, although I could make a guess. We've got this going on. Again, this is not a perfect sketch, and it doesn't have to be perfect. And then down here, there's a, whoops, that's supposed to be more curvy. All right, very good. I want you to try it one more time. Let's pause the video, find the asymptotes if possible, so create the framework, and then we'll come back and graph. Okay, here's my work for the second problem. The top of this one is factorable. In fact, it factors to x plus 2 times x plus 2. So there is a removable discontinuity, or a hole in this one, at the spot where x is equal to -2. Other than that, the graph of this function is going to behave like this line, x plus 2. So I plotted that line, and I showed the hole here. I want to verify to you that there is indeed a spot where this is not defined, so I'm going to go to a table, second, and window to set up a table at -3, and then go by 1. That'll show me just what I want. It's second and graph, and you will see right away when x is equal to -2, error. There's a divide by 0 error there. You cannot have that guy. So there's our hole. Ladies and gentlemen, that wraps up this lesson. I'm going to ask you to get out there and do the U-try at your earliest convenience, and we'll talk about this in school.